My speech is called Inside the Next Generation of Magnetic Materials, and I come from university, Uppsala University, where I'm an associate professor in Sweden. And I will discuss a little bit what we are doing right now when it comes to research and development, when it comes to looking at different magnetic materials. So this is what I'm going to talk about today. I'm going to talk about rare earth metal-free permanent magnets and give an introduction to the topic, and also, of course, the neodymium price development, which kind of started the look for new materials. I will also go into material properties and compare a few different materials. And then I will go into machine design and discuss how we can change our machine design depending on what kind of material we have. Then I will present two examples on the work we have done on Ferrite generators. And then some conclusions and some time for questions. And you will be able to follow where I am at in the presentation on the left side here. Okay, so I come from a division that is kind of working with very applied research. So we work with wave power, wind power, and marine current power. And we actually build prototypes, and we even want to build prototypes that's full scale if possible, and do experiments and try how they work. And we also have a lot of spin-off companies in these different areas. So we try to also bring the products out on the market. And we work with vertical axis wind turbines, which is kind of a different type of wind turbine. I'm not going to go into that much about that, but we have the generator on ground level. So that's quite convenient, especially if you happen to have a heavy generator, which I will come into later. We also work with vertical axis turbines for marine current energy. So we can put these power plants in a stream or in a tidal water and harvest energy. And this is the first prototype that was installed in March. And here is how it might look when it's on the seabed. And then we also work with wave power. This is based on a buoy as a point absorber. And when it moves up and down with the waves, it will pull the translator of this linear generator also up and down. And this is maybe the most mature of these products if we look at the spin-off companies. So we're actually building the first 42 wave power plants right now, or wave power units for a farm. And it's going to be 420 wave power units in this farm. It's ordered by Fortum. It's going to be placed outside of Sweden. So that's quite a big project. And for all these different energy devices, we use direct-driven permanent magnet generators. And when it comes to direct drive, the generators are quite big. So the permanent, and we also have quite a lot of permanent magnet material in them. And therefore, it's quite interesting for us to look at permanent magnet materials. And we have, for 5 years ago, we only looked at neodymium-based magnets, but now we're looking at some options. So we're trying to find some rare earth metal-free options. And why do we want to do that? Well, first of all, the price development. I will show you a picture of that later, but I think you are probably all aware of the problems with the price when it comes to neodymium. We also have the environmental aspects, both for the environment as such, but also for the work environment, for the people working in the mines. Also, it's a politically unstable matter, since most resources comes from one country, and it's connected also to the availability. 95% of the resources are in China, and there's actually quite stunning report here from Reuters, which I found, where they said that China could be a net importer of rare earth metals in 2014. That would be quite interesting. And the scenario is quite similar for neodymium, praseodymium, and dysprosium. So it's quite interesting to look at options then. And if we're looking at options for generators and motors, of course we can look into an optional technology. We could have electromagnets. However, then we would lose all the benefits with having permanent magnets. So we would get more rotor losses, we would need to electrify the rotor, we would need more maintenance, etc. Another option would be reluctance machines, and I know that is especially investigated for electrical cars, to use reluctance machines. But we are then looking instead on optional materials. And what we have been mostly looking at so far is an old material, the ferrite, which actually has come, the new grades are quite good. And we also have some other modern materials apart from neodymium iron boron, like samarium cobalt. However, they are also rare earth metals, so we'd like to not use them. And then we're also looking at new materials together with some material researchers at the university. And here I call this new material NewMat, because we don't really know how it's gonna, what material it's gonna be made of yet. So this is a graph, I think you've probably seen it before, on how much the price increased this summer of 2011. And the price of neodymium metal increased more than 1,000% from the summer of 2009 to the summer of 2011. And this makes this business quite difficult, and the price is difficult to predict. This summer, I guess, was kind of the starting point for looking at rare earth metal-free options for permanent magnets. And now the price have decreased quite a lot. It's still quite high compared to the levels where it was maybe 2007. It's about 61 euros per kilo this month or last month. But it's varying. It has been varying a lot. So therefore, we would like something more stable. So I'm going to talk a little about material properties and compare some different materials. So I just wanted to go into some of the important characteristics or parameters for the materials, which is the remanence, the remaining magnetic flux density in the permanent magnet, and then also the coercivity, especially the intrinsic coercivity, which is the external field for which the magnet is permanently demagnetized, and it could be partially or totally demagnetized. So then we lose its remanence and it's not a permanent magnet anymore. So that's really bad. And then the energy product is quite important, since it will tell us how much magnets we need. It's the energy stored in the permanent magnet. Some other properties that are interesting to look at if we're going to compare materials is the strength of the material. Some materials are quite brittle, and especially when they're mounted, we might get cracks in them. So the mounting procedure is usually the most challenging part. We also need to know if we need corrosion protection. Like neodymium-based magnets usually need protective coating if they're not placed inside some cover. So it depends on the geometry as well, but usually you need some coating. So if we're going to then compare some different permanent magnet materials, we need to consider these magnetic properties. We also need to consider electrical properties, such as electric conductivity, since this will affect how much eddy currents we might develop in the rotor or in the permanent magnet especially. Since eddy currents are losses, and they will also heat up the material, and a lot of the magnetic properties will get worse when the material is heated up. Not all, but most. When it comes to mechanical properties, material strength and also density, how much volume we need for a certain weight, and also the corrosion then. So here we're then comparing neodymium iron boron, which is kind of the base, since that's what at least we used to use. And then we compare it to ferrite and to this new material. And the neodymium iron boron has a high remanence and also a quite high intrinsic coercivity. So it's very well protected against the magnetization. And it has a high energy product, so we get a lot of magnetic energy per kilogram or per cubic meter. When it comes to ferrites, if we look at this, one of the new grades, Y40, it's actually quite good. It has a remanence of 0.45. So it's better than the old ferrites, but it's still about 3 times lower than the neodymium magnet. The coercivity has also been increased somewhat compared to earlier products, but it's still quite low. So depending on the application, this needs to be considered. And the energy product is then quite much lower than the neodymium energy product. This new material is one that my colleagues are looking at right now, where they think they can reach quite a high remanence, but they have some difficulties on increasing the coercivity. So this is some values that we think we might be able to reach. And the energy product is quite optimistic. It might be more about 150 or 100. But it's 1 or 2 times less than neodymium. And if we then look at some material properties, like the material strength, we know that the ferrites are quite brittle. So we need to consider this when we mount the magnets, for instance. However, since they are not as strong, they don't have as high magnetic energy, they might be easier to handle. When it comes to corrosion protection, it's quite bad for the neodymium magnet, as I said, so we need some coating, but the ferrite is quite good. And then the electric resistivity, which is then the inverse of the conductivity, is very high for the ferrites, so we won't have any eddy currents developing in that material. We might have some problems with eddy currents in neodymium-based magnets. I don't have numbers for these things for the new materials, but the density would be somewhat close to neodymium, where the density for ferrites is a little bit lower. So then the more interesting part, then, if we're going to compare what we actually get when per kilogram here. So we have the energy product for the 3 different materials, and we have the density. So we can then find an energy density in joule per kilograms. So we see that it's about 41 for neodymium, about 8 for ferrites, and about 27, maybe a little lower, for this new material. And we can then calculate a relative required mass. That would be if we have a neodymium-based generator as a starting point. So we look at the mass relative to the neodymium mass. We need 5.2 times more mass of ferrite, and about 1.5 up to 2 or 3 times the mass when we use this new material. So this is quite a problem if we want to limit the weight of the generator or motor, that we have to have 5 times as much mass for the ferrite generator if we want the same magnetic energy. And if we then put in price into this equation, this is some quotations for a 200 kilowatt wind generator, so it's quite large magnets, large pieces, which are a little more costly to produce. It's about 25 euros per kilo for the neodymium-based magnets, and about 1 euro per kilo for the ferrite-based magnets in the grade Y40. So then we can get a relative energy price. How much magnetic energy do we get per euro? And if we normate this as 1 for neodymium, we only pay 0.2 for the ferrite. So for the same amount of magnetic energy, we only pay 1/5 for the ferrite magnets, whilst we pay them 5 times more for neodymium. And we don't have any price for this material yet. However, if this material is going to be comparable and be able to work on the market, it needs, of course, to be quite cheap as well, which is a challenge, of course, for the material researchers. But again, the mass is 5 times more for the ferrites, so that's a disadvantage. in most cases. So if we then go into machine design instead and try to see what can we do with the machine design to adapt it to different magnetic materials. Well, we need to consider what machine properties will affect the permanent magnet choice. And one of them, which is not here, is of course, and if we have any restraints on volume and on weight, because that will of course have a big influence. Then we need to consider if the machine is going to be a motor or a generator, what rotational speed we have in case we will have large centrifugal forces that needs to be considered, what electrical frequency do we have. For these renewable energy applications I showed you before, we have around 10 Hertz for most of them as rated with frequency. So that's quite low, and also the harmonics then also get quite low. So we don't have that much problems with eddy currents, for instance. We also need to consider the operating temperature and cooling system. How hot do we allow the machine to get? What can the magnets handle? Most magnetic properties get worse when heated up, some don't. Like the remanence can decrease, the coercivity can decrease, but the coercivity can also increase, so that depends on different materials. We also need to consider the current peaks to make sure that we don't get a field from the stator in the generator that is higher than the intrinsic coercivity. And this will depend on the current level, short circuit currents, and also the electrical system and control, like what kind of current do we actually take out of the machine. Harmonic contents needs to be evaluated as well, again to see what kind of eddy currents we get. If we have a lot of harmonics, we might also get a lot of eddy current losses. So if we then look at how different rotors could look, well, if we're going to use a standard design with stator steel, the desired magnetic flux density in the air gap is somewhere around 1 Tesla in order to use the steel as a field reinforcement. And if we then have some low remanence, we need to reinforce the field somehow from the rotor to the stator so that we get this higher magnetic flux density in the air gap. If we have a low intrinsic coercivity, we also need to have some field protection so that we can protect the magnet from the adjacent field from the stator. So here are some examples of how different rotors can look. We have 3 different designs of surface-mounted magnets, which is the most common design. Here we have a design with the tangentially magnetized generator. And here we could actually have much longer magnets that goes longer into the rotor. I'm going to show you an example later, so that we could actually reinforce the field by using this design. Then we have several innovative designs here on how you can have interior magnets. However, you also need to consider how you're going to mount this and how you're going to produce it, because it might actually, some of these might be quite difficult to build. So if we look at the neodymium-based generator again, we have a high remanence, a high coercivity. So we don't need to have any flux reinforcement, and normally we don't need any extra protection against fields. So we can have the magnets radially magnetized in this direction and surface mounted. And that's the most common way for the neodymium-based magnets. One disadvantage, if we want to use rectangular magnets, which is the cheapest to buy, we don't have any possibility to shape the field with the pole, which we have in some other designs. If we look at the ferrite then, we have low remanence and low coercivity. So we need to have some kind of flux reinforcement, and we need to have some kind of protection against adjacent fields. And one option is then to have them tangentially magnetized, so they're magnetized in this direction and buried into the rotor. So we have the flux coming out like this, and then it goes through this narrow pole shoe, which kind of narrows down the field, so the magnetic flux density becomes much higher. So here we can achieve about 0.9 or 1 Tesla in the air gap. just as we desired, by reinforcing the field with this pole shoe. And also the magnets are quite protected down when they're inserted in the rotor like this. However, as I said before, we need to consider that the mass will be 5.2 times as much. Also, the volume is even more, since we have less density for the ferrites. So we have even more magnet volume. So the rotor becomes quite large. One advantage is that we can shape the pole shoe here, this one, so that we can get the optimal shape on the field and still use rectangular permanent magnets, which are mass-produced. That's quite good. If we then look at this new material instead, we have this high remanence but a low coercivity. So here we don't need any reinforcement because we have quite high magnetic flux density, but we need to protect the magnets somehow. So then we can have them radially magnetized, so they're magnetized in this direction, but they're buried, so we have some iron in front of them that can protect them from fields. So that's one option to do it. And then we would again have about 1.5 or maybe 2 or 3 times the mass of neodymium magnets. And we also here get the option of shaping the pole and therefore maybe get a better field shape, and also still use rectangular permanent magnets. When it comes to the ferrite rotor, we have some design issues we need to solve then. Of course, we need to achieve this high magnetic flux density in the air gap, so we need to somehow reinforce the field. We need to consider how to mount the permanent magnets, because it's quite difficult to mount them in this round shape. Also, we need to consider the increased mass if we compare it to a neodymium generator, for instance. This will, of course, lead to that we need more supporting materials, we need other bearings, we will have a different shaft to vibration eigenfrequency, so it will change the machine quite a lot if we change the neodymium magnets to ferrites. Also, it will affect stability and control, but that might actually be beneficial. For example, for a wind turbine, we will get more inertia, so it will be less change speed, a little slower, which might be good. We also need to consider the risk for demagnetization, since the coercivity is quite low. And also, we might actually want a larger diameter than to fit all this volume inside in the rotor, compared to for the neodymium-based generator. So I'm going to give you some example. I did a study last year to compare a generator for wind power and to see if we could get the same electromagnetic properties if we had a ferrite generator compared to a neodymium-based generator. And the idea was to have the same stator and just change the rotor. And this generator was to be built or designed for a vertical axis wind turbine of 200 kilowatts, so it could be placed on the ground level. So the weight increase didn't matter that much. So this was presented at the conference last summer. Also, we don't have any pitch of the blades for this wind turbine, so therefore we need to control the whole turbine electrically. So we need a quite high overload capacity of the generator, so it's a little bit over-dimensioned, and therefore we have quite a large amount of permanent magnets. So this is the result. And here you see the first generator. We have the same stator in both cases. And this is then the surface-mounted neodymium iron boron magnets. And here we have again the ferrite magnets tangentially magnetized between these pole shoes. And these two are then very similar in properties. You can see the differences in volume. And if we then compare the electromagnetic characteristics, we see that they are very similar. We have a few differences here in italics. The maximum torque, the cogging, the load angle, and the air gap force are differing a little bit, but not that much. So we have actually achieved to design a generator with pretty much exactly the same electromagnetic properties. However, of course, we have one big difference, and that's the mass of the rotor. And in this case, we used a grade Y30, which is a little lower energy product. So we got a permanent magnet mass that was 8.6 times higher for the ferrite generator. And the rotor weight was approximated to be about 3.3 times higher. So that kind of changes a lot. However, if we would have, we see here that the Y30 has energy product which is about 75% of that of Y40. So if we would do this study with Y40, we would get better results when it comes to the weight. However, for this vertical axis wind turbine, it's actually not a big problem with this increased weight, so we can handle that. But for a horizontal axis wind turbine, we wouldn't want to add a 3.3 times heavier rotor, probably. So that's a bigger problem then. So the conclusions from this comparative study was then that it was possible to design this ferrite generator with the same or similar electromagnetic properties. And when the weight is less of an issue, ferrite seems to be a viable option. And also we had an idea then that if we would mass produce this kind of generator with the same stator, we could actually change the rotor comparing to the current neodymium price. So we could have a ferrite generator rotor sometimes and a neodymium rotor sometimes for the same machine and the same stator, and with everything else being similar. The second example here is a wave power plant. And as I said before, we have this buoy connected to a line and then connected to this translator inside a linear generator. And this buoy pulls up the translator when the wave moves up with the wave, but then when it moves down with the wave, this line actually slacks. So we need to somewhat overcome the electromagnetic forces in the generator and pull down the translator, which we have solved with springs. But then in the next generation, we looked at a large mass instead. So we had a big ballast here in the bottom, just to pull it down. So then you think, okay, why don't we add a heavier permanent magnet material instead, since it's actually beneficial with a large translator weight in this concept. So this is actually a perfect generator to look at for the ferrite option then. So this is a first design of a ferrite linear generator. And here we have, since it's a linear generator, we can have rectangular pole shoes and rectangular magnets. So it's quite easy to produce because you just have these rectangular pieces. So it's quite easy. It's much more cheaper than to make these pool shoes otherwise. And here are some pictures from the mounting of the first linear ferrite generator. The first one that we know of, at least. And this was installed in March 2013, so we're kind of starting to look at the results from it now. But the mounting was quite, it actually went better than we expected with all the magnetic forces and to consider everything. Okay, so some conclusions of this presentation then is that it's important to find alternatives to neodymium and other rare earth metals, and especially from this environmental reasons, price, availability. We need to have something that is more, we know what we're going to get in 5 years as well. And ferrites are then a viable option. However, we need to be able to accept the increased weight, as we are in the vertical axis wind turbines and in the wave power plants, it's fine, but for other applications it might be worse. And then we need to be able to handle this lower corrosivity as well, and that also depends a lot on application for the machine. So currently, rare earth metal-free materials are being developed. So we see a future outlook for the rare earth metal-free permanent magnet electrical machines. And what can we do next, and what can you do next if you are machine designers then? Well, you could consider ferrites then an option for your applications and see if would it work with the increased weight and lower corrosivity, depending on application, of course. And then there's also the option to wait out these new materials. There's a lot of research going on now, both in Europe but also in US, on finding rare earth metal-free alternatives. So hopefully something is gonna come out on the market in a few years. And then of course there is the option of changing the design, maybe go for electromagnets instead.